Morning everybody. To do the last bit of this complex numbers chapter, it would be really useful to know some stuff about Maclaurin Series first. So we're just going to do a couple of lessons on Maclaurin Series, and then we'll finish off the complex numbers chapter the week back after half term. After that we've only got a vectors chapter to do, and we've done almost half of the year 2 pure stuff actually, which is quite surprising. Anyway, it is what it is. I'm just going to, because I'm not with you guys here, it's a bit difficult to try and derive this for you without being able to speak to you directly. So I'm just going to tell you what it is, and if we get some time when we're back at school, we'll look at where this thing comes from. So a Maclaurin series is as follows. So basically it's an approximation to a function. So if I've got f of x, then a good approximation to this would be f evaluated at 0 plus f dash 0 of x plus f double dash, so that just means the second derivative, x squared 2 factorial plus the third derivative, x cubed over 3 factorial, and this just goes on and it's an infinite series. So one thing you can do if you want to try and get an idea heuristically of why this works, if you so if you want to see one of these, what you can do is try, so using a graphing application, try f of x equals to e of x, e to the power of x. So if you just do f of 0, then if you do f of 0 plus f dash 0, oops daisy, x, and then you plot the next one, oops daisy. So if you plot this graph, then if you plot this graph, then if you plot this graph, and then plot y equals e of x on the same graph, you'll see that these are slowly becoming better and better approximations for the exponential curve. Okay, so just before we go any further, there's a lot of differentiation involved here. So a few things to note. Once you get past a third dash, you're going to start getting really tired of writing dashes. So instead of writing 3 dashes there, you can write a 3 instead. Similarly, you could have written a 2 there for squared. So third, fourth derivative, fifth derivative. You can just write the number instead of writing the dashes. Also, in this chapter, you'll come across some derivatives you haven't come across before. So you'll come across deriving cosine x. I don't think you come across differentiating that with a factor before the x. No, you don't, I don't think. But I'll tell you what it is anyway. So if you've got, oops, daisy. So if y is equal to cosine k of x, then dy dx is minus k sine k of x. Also, if you've got y sine k of x, then dy dx is k sine k of x. And if you're interested, in the first instance, the derivative of sine of x is, oops, that should be a cos, is cos of x. And the reason why there's k out the front is because I've used the chain rule. So the derivative of sine x is cos x. If I've got k lots of x in here, by the chain rule, I get k lots of cos kx. And I think only one other thing which you won't have seen yet, I don't think you've seen this anyway, is log k of x, the derivative of this, is just 1 over x. And that's true for all values of k. The reason for that is to do with the chain rule again. in general, the derivative of log x is 1 over x. So derivative of log k over x is 1 over kx times k. So the k's always cancel each other out. So I think that should be sufficient amounts of differentiation for you. Maybe just one other one to mention. If you have something like y equals log of 1 plus x, then dy dx is going to be, well, log of x, the derivative of 1 over x. So if I derive this, I get 1 over 1 plus x. And then if I times through by the derivative inside here, well, derivative of 1 is nothing, derivative of x is 1, so the derivative is just 1 over 1 plus x. So let's try an example of this. Find the first three non-zero terms and the general term, the Maclaurin series for sine x. So f of x is sine x, and f of 0 is 0. F dash of x is cos x, and f dash of 0 is going to be 1. If I now differentiate cos, I'm going to get minus sine x, and again I'm going to get evaluated at 0 gives me 0. Okay, if I differentiate minus sine x, I get minus cos x, so f differentiated 3 times gives me minus cosine x, and evaluating that at 0 gives me minus 1. If I now differentiate this, hopefully you'll start to see the pattern now. If I differentiate cos x, well, if I differentiate cos x, I get minus sine x. So if I differentiate minus cos x, I get sine x. And I'm back to where I started, at the top here. So, I'm not absolutely sure how many of these terms I need. Oh, actually, I need the first three non-zero terms, don't I? So far I've got 1, 2, so I need a third one. I need f of 5 as well. And f of 5 is going to be the same as f of 1 because I can see how this is going. It's that pattern, sine, cos, minus cos, sine, cos. It's going to repeat that pattern every 4. So I don't need to go any further with that. I can just write it down if I want to, just for completeness sake. It also asks me about the general term. Well, f of, let's say, well, if I said f of r, then I might be able to deal with my sine and coses. However, I've got some minus issues as well. So what I'm going to do is say f of 2r. So f of 2r is going to be minus 1 to the r sine x. So what's going on here? Well, so this is obviously not been differentiated at all, so I could almost feel like a 0 there. So 0, 2, 4, so all the even terms I've got sine x's on, so that's why I've got a 2r here to go for the evens. And I want to go positive, negative, positive, etc. So anything to the power of 0 is 1. When it's for the second one, that's when r is 1. So 1 is here, so that's going to be a minus 1, etc., etc., etc. So the 2r makes sure that they're even, and this r here just keeps that minus 1 going between 1, minus 1, 1, minus 1, 1, minus 1, etc. So that would be the general term for that one. And I can evaluate that at 0. If I evaluate that at 0, I've got f of 2r x is equal to 0. That should be a 0 in there. And if I want the odd terms, well, I use 2r plus 1 for the odd terms. So I know it's going to be cos x every time. And with this one, I'm going to be, well, the first term for when r is 0, I want it to be positive. So when r is 0, I want it to be positive, so minus 1 to the r works for this too. And if I start going through the r's, this will become minus 1, then 1, then minus 1, then 1, etc. F of r to a f to 2r plus 1, evaluated at 0, well, cos x, oops, a daisy, I didn't realise that was off the screen. Cos x of 0 is 1, so that just leaves me minus 1 to the r. Okay, so what I can do now is write out my general Maclaurin series and then fit these things into where it goes. So the general Maclaurin series is f of x is equal to f of 0 plus f dash 0 of x plus f double dash of 0 x squared over 2 factorial plus dot dot dot, and it just carries on going. So we're trying to find sine x. So sine x is equal to, well, we know that all of the even terms are 0, so I can just fixate on the odd terms for now. So f dash of 0, we found it earlier, was 1. So I'm going to get 1 times x. And then f double dash of 0, I don't need that one. I need the third one, don't I? I need f triple dash. F triple dash was minus 1. So we've got plus minus 1 times x cubed over 3 factorial plus, and then it's going to be 1 times x to the 5 over 5 factorial. I'm just ignoring the odd, sorry, the even terms because I know they're all 0. And then if I think about what the half term is going to be, then that's going to be, let's write it on the next line so I've got a bit more space. Well, I know evaluated at 0, it's minus 1 to the r, and it's x to the 2r plus 1 term. We said for that r to be true. And if I've got a 2r plus 1 up there, similar to these, I better have 2r plus 1 on the bottom factorial to compensate for that one. If you're not convinced by this, then just try this with these ones and just check that it does actually work, and hopefully that'll convince you. It's a little bit of practice sometimes generating these. So just always think about this bit first. What does this have to be? And then this will normally quite easy to find. So that's let's just tidy that up slightly. So we've got sine x is equal to x minus x cubed over 3 factorial plus x to the 5 over 5 factorial plus minus 1r x to the 2r plus 1 over 2r plus 1 factorial. Okay, so what I'd like you guys to do is try some questions on these. Can you try exercise 6.1, and can you do questions 1 through to 5? If you have any issues with this, please give me a shout, and I'll try and get back to you today or tomorrow. Have a good day, have a good half term, and I'll speak to you in a couple of weeks' time. Bye-bye.